Okay, I'm almost there. I only see one person around this time. Hello, Michael.
Hi. Hi. How are you?
Hello. You guys have any questions about the course? Hi, Jane.
Hi, Professor.
Hello. Why don't you guys turn on your video so that I can see your face? Hi, David. Hi, Michael. Hi, Jane. Are you in the office now, Jane? Are you working in the office? That's why you have to put on a mask? Yeah, I was disconnected for a short while. I don't know why. I hope this is okay. This is stable. And let's hope that things are stable the way it is. Okay, let's get started then. If it's unstable, if the network is unstable, please let me know. I will switch to using another network if possible. Okay, so let me share my screen. And let me share my PPT slide. Can you see my slides? Okay, very good. I can see that some of you are nodding your head, which is a good sign. Today, I'm going to talk about high-frequency solutions and Gaussian beams. Okay, and these are very, very useful solutions because they approximate, but yet they offer great physical insight. They are especially useful in the optical regime where the wavelengths are very short. Okay, so the first thing you can make when the wavelength is very short is called a tangent plane approximation. In the tangent plane approximation, you assume that a wave is locally tangent to a surface. So you can say that this is a tangent. This is usually called tangent to a surface. And if the wave is locally tangent, then you can more or less assume that the surface is flat. Just like many of us thought that the surface of the Earth is actually flat because the radius of curvature is so huge that we don't know that the Earth is actually very, very curved if you look from far away. It looks like a sphere. And so when the frequency is high, you can make these tangent plane approximations. And this is especially true when the frequency is high or the wavelengths go to 0 and the frequency is high. Then you can apply what is called a local Niels law. To assume that things are locally flat, and this kind of thing is actually done a lot in the movie industry. For instance, if you have very, very complicated objects in a room, and instead of solving this problem approximately or exactly using computers, you can actually make tangent plane approximation and do ray tracing. Okay, this is called ray tracing. In other words, you assume that the plane wave becomes a ray. And as the plane wave bounces around in a very complicated environment, it behaves like a light ray. And you can trace the light ray and figure out how things should be looking like in a room. This is done a lot in the movie industry. To make things look realistic. Okay, so I might have a picture of that somewhere. Let me see. If I were to show it to you, then let me see. There's a problem advancing the thing. Yeah, this is the consequence of ray tracing. And by doing ray tracing, you can make things look very realistic in the picture. Okay, and as you can see, this is an important part of the movie industry these days. Let's try to go beyond ray tracing. One of the obvious things that you can do about ray tracing is actually to do lens optics. Let me pull this back again. And in lens optics, you just assume that if you have an object, it gives out light rays, and you can trace the light ray as they go through a dielectric object. And you can apply local Niels law. And you can even use Fresnel coefficient to estimate the amount of transmitted light. And you can actually figure out the intensity of light here using ray tracing technique. And this is done a lot in the movie industry, as I mentioned to you before. And this is usually used if if this object is of size d, and if lambda is much, much less than the size of the object, then you can make the short wavelength approximation, which is also called a geometrical optics approximation. Sometimes called GOA in short, or just GO in short. Okay. You can actually figure out refraction and transmission quite easily in this kind of thing. And one of the other things I like to talk about is actually Fermat's principle. Fermat's principle is formulated around the 1600s for ray optics. And I like to point out the fact that Niels law It's also known in the Islamic world about 984 AD in the Islamic world. Okay, so what is Fermat's principle? Is a principle based on least action. It says the fact that if I have a very complicated object, if I have a light ray, okay, you have a source, you have a ray, the ray is going to bounce around, or maybe in this manner. I'm just drawing a cartoon picture, and it takes the minimum time delay. So in other words, if you were to send a pulse from a source to the observation point O, the time it takes to travel from point A to point O is minimal in terms of time travel if you were to make the optical pulse into a pulse. And time delay is also the same as minimum phase delay. Okay, I get the sign that my internet connection is not stable again. I'm going to switch on to another network in my home. Hopefully that I will get more stable connection. You're going to be disconnected temporarily when I switch over to another network. Okay, I hope that the stable connection is with us now, that I wouldn't get this warning message that my internet connection is unstable. Anyhow, so, you know, a time delay in the time domain is the same as a phase delay in the frequency domain. So when you have a pulse that can travel with minimum time delay from point A to point O, you can also show that it corresponds to a pulse that travels with a minimum phase delay. And that is the principle of least action, okay? And nature has it that nature is very efficient. Nature always does thing with the least fast. And with the least fast in the sense that when you travel from A to O, the phase is actually minimized. I don't know how nature does it, but nature seems to know that, and people in the 1600 knew about this, and they formulate the principle of least action to describe many physical interactions. Okay, so how do we use this Fermat's principle to solve problems that are related to lens optics? You can do it this way. We can actually arrive at what is known as Generalized Niels Law quite easily by assuming that you have a point A, B, and C, and they are connected by light rays. Light rays can be thought of as plane waves. Okay, this is a light ray. And you can have another one here. And you can think of them as being locally plane wave or local plane wave. Because you can think of a source. If the source is producing a wave, it produces a spherical wave. Okay, you can think of this as a source. And when you have a spherical wave, if you observe at this point, you essentially see a local plane wave. A local plane wave is just a light ray. So when you see a locally plane wave traveling to you from a point source, which is actually in terms of a spherical wave, you can call that a light ray. And then the phase delay that it gets from A to B can be written down rather easily. And then the phase delay from B to C can be written down also rather easily. And we can write down those phase delays, and let me write them down for you next. Okay, so based on this picture, the time delay or the phase delay which is also the same as time delay, would be P, let me call that P, the P will be the phase delay, which is the product between the K vector in the incident ray times this vector R sub I. Okay, that will give you the phase shift of this wave as it travels from A to B. And then as it travels from B to C, it will suffer or accumulate another phase delay, and that phase delay is given by KT dot RT. KT is this vector over here, as you can see. RT is this position vector, and this will be the total phase delay. And let's assume that I'm going to change Xi a little bit. Okay, I'm going to change Xi a little bit. And if you go back to this picture, I change Xi a little bit. And if this is the minimum point for phase delay, it would be a stationary point, which means that if I were to change Xi a little bit, there's no change in the total phase delay, because by Fermat's principle, it will find the path with the minimum phase delay, and hence it's a stationary point. Okay, so the path of minimum phase delay is a stationary point. So if I were to find the change in the phase with respect to Xi, it should be 0 because it is a stationary point. And then now you can write this out explicitly. Okay, you can write this out explicitly. Then you can actually show that P as a function of X will be KIX XI, okay, for this part, and then the other one will be KTX XT, okay, and we say that Zi remains constant. Zi is constant. So if you look at this formula from this picture, if I were to change Xi a little bit, Zi remains constant. So I need to change the variation of P with respect to Xi only, since Zi does not change. Zi is in there, but I'm going to leave them out. Okay, so I finally, when I differentiate this, I get the fact that Xt, as you know, Xt plus Xi is a constant in this picture. If you look at this picture, Xi plus Xt is a constant. So when Xi changes, Xt changes also by the negative amount. So if I were to differentiate this with respect to Xi, then I will get KIX. But the second term, I will get KTX because Xt plus Xi is a constant. And so I have this, by Fermat's principle, KIX must be equal to KTX. And this is just Snell's law, that the X component of these two K vectors should be the same. Okay, this is just phase matching or Snell's law. Or Snell's law. So this is a wonderful result because it's obtained not using phase matching, but with the argument that the phase delay or the time delay between the point A to C should be minimized. Okay, and if you write this out in terms of angle, it will be Ki sine theta I would be equal to KT sine theta T. Okay, this is what phase matching says, and it's just what we know as Snell's law. So are there any questions regarding the use of Fermat's principle? Okay, so this is wonderful news. It says that in the high frequency regime, when we can think of this as rays, we can write down the solutions rather simply, and we can use this concept to design meta surfaces. just imagine that you have a surface here where you can affect the phase change on this surface. You can actually cause the light ray to have negative refraction when the light ray comes in this way because of this new Fermat's principle of Niels law. We can get the light ray to bend this way, and at the second interface, it will just follow the ordinary Niels law and bend this way. Okay, let's see how this is done. Okay, so this work was actually done by Federico Capasso of Harvard, and you can read about his work, which is pretty well known in the community. So instead of saying that the phase delay now is just the simple Ki dot Ri plus Kt dot Rt, okay, that we have a phase screen. Let's call this a phase screen. And it's made from meta surfaces. It's made from meta surfaces so that when the light ray goes through this phase screen, depending on where you are, the phase shift gained by the wave is position dependent. It depends on where you hit the phase screen, how the light ray hits the phase screen. And so what you have is something rather interesting, that you have a light ray, it comes in with Ki, okay? But then there is a phase screen that causes the light ray to add an additional phase due to where the light ray is hitting that surface. The light ray can be thought of as a local plane wave. And this kind of problems are usually not solvable in closed form. You can actually solve this problem using numerical software, using the field called Computational Electromagnetics. We'll learn about computational electromagnetics later on in the course. Essentially, it says that given Maxwell's equations, no matter how complicated the geometry is, we can solve Maxwell's equations with respect to this kind of very complicated geometry. Hence, we can send a plane wave coming into this geometry and study the phase shift of the plane wave as it goes through this phase screen and actually ascertain what this phase function should be. And the wonderful thing is that light ray has a, like if you take blue light, like your blue disk or blue laser disk, the wavelength is about 400 to 500 nanometers. But nowadays, nano fabrication is so wonderful. For instance, we can make transistors. They are about 10 nanometer in size now. Okay, so we can make a lot of wonderful things that are very, very small, much smaller than the wavelength of light. And if you work in an expensive lab, you can do nano fabrication. I believe our Berkeley Nanotechnology Center has that capability. You can fabricate this kind of tiny, tiny structures, made of maybe gold or silver or some other metallic structure on top of a surface. And hence you can think of this as being sub-wavelengths, very much smaller than the wavelength. And you can think of them as behaving like a phase screen. You can solve this problem with computational electromagnetics. So if this is your new equation for phase, then what you have is that according to Fermat's principle, then if the light ray is hitting the surface correctly, then you will get Kix minus Ktx. And then there will be an additional contribution from the phase screen now. And all those have to add up to 0 according to Fermat's principle. If that point of interception is the point of minimum phase delay. Okay, so So you can use this kind of things to do wonderful things like a flat lens. Because you can actually get negative refraction if you have a source here, and if you have a meta surface, you can get the light ray to suffer negative or to go through negative refraction. And this is your new focus. And this is the source. Okay. Hence, you can make lenses that are very, very thin using meta surfaces. Okay, very, very thin lens. And if you're interested to find out more about this, you can visit with Professor Vlad Shalev. He's doing research in this area. So is I find remembering her name a little bit difficult. Alessandra Botashiva, I think. I'm not sure about the spelling. Okay, they're in the nanotechnology lab in Berg Nanotechnology Center, and you can talk to them. Okay, and this is what gave rise to what we call the generalized Niels Law. Okay, because of this additional term we have over here. Okay, so are there any questions regarding this? Well, if not, let me move on to talk a little bit more about computational electromagnetics, on how to solve this kind of problems involving very complicated geometry like this. And what you do in computational electromagnetics is to actually use periodic structure. It turns out that if you make all these things out of periodic structures, then the problem can be simplified. We don't know how to solve this problem in closed form. All the things that we have dealt with in this course assume no such structure. However, if we can use Bloch-Floquet theorem, you can actually solve for the scratching solution for such a structure. What it says is that once you have a wave coming in, the reflected wave is not just one single ray. What you have is actually the reflected ray is being spread out into multitudes of rays. Okay, so these are called Floquet mode. Instead of just a single mode. And then by solving this problem using Bloch-Floquet theorem, you can ascertain the phase shift. The phase shift as a function of x and y. That is, if I were to arrange these structures, and if they are arranged in a specific manner, what should the phase shift be? I can obtain the phase shift by solving this problem using computational electromagnetics, and then I can use some commercial software to solve this problem. Okay. Are there any questions so far on generalized Niels law? If not, let's move on to something more interesting, which is Gaussian beams and the derivation of the Paraxial wave equation or the parabolic wave equation. Okay. You have seen Paraxial physics before in your course. That is when you were studying waveguides. Say if I have a waveguide, and one of the things that you see is that the wave is guided by a bouncing wave. We have a bouncing wave picture. This is how wave is being guided. You can even think of a dielectric slab waveguide being guided in this same manner by the bouncing wave picture. However, when the frequency is very high, you probably know that omega square mu epsilon must be equal to beta z square plus beta x square. If I call this z, and then call this x direction. You can probably remember that this is beta z squared plus m pi over a squared or something. The x direction has to be discretized. You can see that when the frequency goes very high, if m is fixed, and omega tends to infinity, then beta z also has to tend to infinity. You can see from this equation quite clearly. So as you sketch this picture, the light ray has to bounce around like this, because if this is a z-axis, beta z has to tend to infinity when the frequency goes to infinity. So this physical picture you can see in your waveguide theory part of the course, and this is called a Paraxial wave. Because the wave is traveling very, very much in parallel to the z-axis, the direction of propagation. Okay, so this is a physical picture of what the Paraxial wave is. And then we can now solve Maxwell's equations using Paraxial wave approximation, as long as the frequency is high, because when you have, say, a source, and then your observation point is over there. Okay, so when the frequency is very high, the light ray very much travel like a ray from point S to point O. Okay, and the light ray is very much in the direction of propagation on the line connecting S and A, and there's very few light ray that are away from the z-axis, and most of the light ray that you receive at the observation point are almost parallel to the direction of propagation. Okay, so these are called paraxial rays, and then we can look for solutions to Maxwell's equations that are paraxial in nature. And let's go back to the fundamentals again. We show that in free space, the vector potential satisfies this equation, where beta is equal to omega square mu epsilon. Okay, and then we also show that there is a scalar potential attached to the vector potential, and the scalar potential satisfies this equation in a source-free medium. So this is a source-free case, and then we actually obtain this by applying the Lorentz gauge. Divergence of A is equal to minus j omega mu epsilon phi, which is called the Lorentz gauge. Lorentz spelled without the z or without the t is very important. Okay, so we are going to look for solutions to these PDEs, maybe just one of them, just this one. Assuming that the light ray is propagating very, very parallel to the direction of propagation. Okay, so I'm going to assume something like this and say that, well, because of the Pyrexia approximation, the vector potential A is predominantly a slowly varying part multiplying by a rapidly varying part. Okay, so this is beta z is large, so that this is rapidly varying. You can see that when beta z is very large, if z is going to change just a little bit, this is the z direction, say. If z is going to change a little bit, I have a rapid phase change, whereas this part is assumed to be slow. Slowly varying, and then you can think of this as a wave propagating in this direction with its phase changing mainly in the z direction, but very later change in the other direction, which means that the light rays are all almost parallel to the z-axis. Okay, so if this is the case, then let's see what kind of approximations can be done. Okay, we are going to assume that we have a simple x component only we just observe the x component of this vector potential, and that it consists of a slowly varying term, which I call psi of r, times a rapidly varying term. So I'm going to assume that beta z is going to be approximately equal to beta in this study, because the wave is so parallel to the z-axis that beta z is approximately equal to beta. And then again, I say that this part is slow, this part is fast, rapid. Okay, so what happens then if I were to solve Helmholtz wave equations again? I would have to have AX satisfying this equation. Okay, and then if I observe this more carefully, then I would have Laplacian of AX being equal to this square plus the Laplacian y square plus Laplacian z square, and then this operating on psi of r e to the minus j beta z. Okay, and this is the only function that depends on z rapidly. Let me focus my attention on this second derivative of this function with respect to z. The others are not that interesting because they're differentiating with respect to x and y, and this is going to be a slow function. Okay, so if I were to look at this rapidly varying part, which is changing with respect to z, then I will find that I have to observe this quantity more carefully. And then using the fact that when I differentiate the product of two functions, you probably learned this from your high school algebra. Okay, when you differentiate the product of two functions, you get the second derivative of the first function times gz, and then 2 times f prime z, g prime z. Prime here means a derivative with respect to the argument, and then you have a third term, which is fz, g double prime of z. Okay, so this is when you use the product rule for second derivative of the product of two functions. Okay, then I am going to apply this now. I'm going to apply, does everybody know this notation that f prime of z is just partial z of f of z? Does everybody know this notation? It's used in some freshman calculus course, but maybe not everybody knows about it. Okay. So if you apply this notation, then this means second derivative, this means first derivative, and so on. So I'm going to apply this thing to here, then I will get three terms. The three terms will be psi of r, okay, times this other term. Let me put the other term outside, okay? And then I'm going to get two terms, one involving the first derivative of one of them. I will get 2j beta d dz of psi of r. Okay, that follows from the second term, because when they differentiate one of them, it brings down a j beta. And then the third term would just give me the second derivative of this function. The first term involves the second derivative of this function. The last term should involve the second derivative of that function. So it gives me beta square psi of r. Okay, and then all of them are still having this term with them, but I'm going to put that outside the square bracket. So if I were to take the second derivative of that, I get that complicated function. And then now I can back substitute this second derivative back into that original function. Okay. And what I have then is that there's a beta square term coming from here, and that would exactly cancel this term. Okay, so if I were to put this back into this equation, Okay, where I have replaced this with that, and then this beta square term will cancel that term, and then I can keep the partial square, partial x square, partial y square term, and finally I arrive at a simplified equation. Arrive at a simplified equation. Let me see. What you have is that the equation will be simplified, and it will look something that looks like this. Okay, partial square, partial x square psi plus partial square, partial y square psi minus 2 zeta beta partial square, partial z equal to 0. Okay, you plug it in here, cancel the terms, cancel this term that can be taken out because it will cancel with this term. And then you arrive at the term involving differentiation of the psi alone. And this equation is greatly simplified because I have also thrown out a certain term which says that the second derivative with respect to z, okay, that the second derivative of this term with respect to z is going to be much, much smaller than this term, minus 2j beta partial z of psi, okay? I'm going to compare these two terms. And this term is going to be much, much bigger than this term. Okay, if I only keep this term and drop this term, I have this Paraxial wave equation, which is what I have written down here. Okay, I only have kept only this term because this term is small. You can see why this term is small because this term involves a beta. Beta is going to infinity. So this term is going to be much bigger than this term. This term is just derivative with respect to psi, which is a slowly varying function of z. So the end of the story is that I have arrived at this equation, and this equation is called the Paraxial wave equation. It's also called a parabolic wave equation sometimes. Okay, and you can solve this equation in closed form as well. I will do that in the lecture notes. But let me go through that very quickly with you as to how we solve this Pyrexia wave equation in closed form. And it's due to using a trick developed by Georges Deschamps. Okay, this is done by Georges Deschamps. In around 1970. He used to be a professor at the University of Illinois. And the trick he used is the fact that the x component or any components of the vector potential must be a solution to this equation, or the Helmholtz equation. And then I also know that if I have my if I put in the Green's function solution to this equation, okay, and as long as r is not equal to r prime, it would satisfy that equation that I have on the first line, or the Helmholtz wave equation. Okay, but how can I ensure that r is not equal to r prime always? Well, I can do a trick. Let me do a mathematical trick by assuming that r prime is a complex vector. It is a complex vector pointing in the z-hat direction, but with the imaginary component jb. Okay, so if you were to put r prime to be such that z prime, okay, this is z prime, and then x prime is equal to 0, y prime is equal to 0. You have put the point source to be located in the complex space, and yet it would still be a solution to the Helmholtz wave equation. Okay, So now I'm going to make a Pyrexia approximation to this expression. Okay, take this expression, assume that r minus r prime, which can be written as now x squared plus y squared plus z minus z prime squared, which would be z plus jb squared. Okay, if you work this out, there would be, this term is actually z minus z prime squared. That's what r minus r prime squared means. Then you're going to make Pyrexia approximation, assuming that x and y are small, but z is going to be large. Z is going to be much, much larger than x. And z is going to be much, much larger than y. So if I were to make this approximation, this term is large, this term is small. So if I were to do that, then I take the z plus jb outside, and then I will have 1 plus x squared plus y squared over z plus jb squared with a square root out there. And then I'm going to make approximations, Taylor series approximation, assuming x and y are small again. And then you can show that this can be written as this one plus x squared plus y squared divided by 2 plus z plus jb. Okay, by doing Taylor series approximation. The moral of the story is that when I make the Pyrexia approximation to this equation, this approximate solution must be the solution to the Paraxial wave approximation of this equation. Hence, I can find a closed form solution to the Paraxial wave equation by using this trick. The algebra is rather complicated. Okay, I will not go through the details, but the details are given in the lecture notes. And essentially, what you have then is that you can find the solution to the Paraxial wave equation in this manner. And I'm not going to go through detail. And this is how a Gaussian beam solution is arrived at. The solution of the Gaussian beam is actually a Paraxial wave approximation of the Paraxial wave equation, and you can obtain that in closed form by using this trick that we have. I don't have time to write down the gory detail, but what happens is that if you were to make Paraxial wave approximation as you have before, you'll find that the wave equation can be written as beta z plus jb over 2 pi. Yeah, this is after lots of algebra. You arrive at this expression that the wave function should look something like this, 2z plus jb. Okay, so this is after you have back substitute this expression back into that original expression, you get something like this, and then you will show that this is equal to e to the minus j beta z finally times a slowly varying term, and this is slowly varying term. You can actually eyeball the slowly varying term out from the above, and you'll find that it behaves like a Gaussian beam. Gaussian beam in the sense that it's Gaussian tapered. Let me see if we can write down the full expression for you here. The details are given in the lecture notes. Okay, the details for this expression is rather complicated. Okay, I wouldn't write it down in this lecture, but I suggest that you read the lecture note and look for the details. And one salient feature that you see from the details is that this wave actually behaves like A0 e to the minus j beta x squared plus y squared over 2r. And then it will have a Gaussian taper component minus x squared plus y squared over w squared. This is the Gaussian part. And then it will have a phase term. This is Gaussian taper. You can see that it exponentially decaying in the x and the y direction. That's what you see of this beam, and that's why we call it a Gaussian beam. But the details will be given in the lecture notes. The catch of this Gaussian beam is given here. Okay, it's taper in the x and the y direction. And of course, you can also solve the Paraxial wave equation using separation of variables, because essentially it's just a PDE. It's just a PDE, and you can solve this equation using separation of variables and then obtain complicated solutions like this. Okay. And then you can also look at these beams in full glory in terms of their graphics, and they will always look very beautiful. And all these beams will have different gyrations, and some of these are called orbital angular momentum because the wave is actually traveling like this. And if it's just a linearly polarized wave, then we call this the spin angular momentum. So this field is actually a very interesting field studied by lots of people around the world because it can have potential applications in very many different areas. So are there any questions before we stop? If you don't have any questions, I'll let you go. Okay, and thank you for coming.
Thank you.
Yeah, I can see some of you, and nice seeing you all here. And thank you for coming. Bye-bye. See you next time.